Okay, now we're going to introduce a totally new electric component. So we've worked with batteries, resistors, and capacitors. Now we introduce what are called inductors. An inductor is very simple. At first sight, it looks like should not do anything to a circuit. It's just a coil of wires. So you have wire that you coil around something. Here you can use what are called, well, you can coil that around a piece of iron, for example, or anything. But the key point here is that you just have this coil of wire here. What's inside here, it doesn't really matter for us. It's just a coil of wire, which is we also call a solenoid. So you have this coil here, and what it looks like in actual circuit, it looks sometimes like this. You see wires here that are coiled around a piece of iron here, in that shape here, or in this shape, or you can have these different shapes here. So basically what an inductor is just a wire that is coiled around several times a small structure. And those wires can be considered to be ideal wires. It's an ideal wire. So there's no resistance here. So at first sight, because there's no resistance there, you might say, so what? It's just a piece of wire. It should not do anything. It's just an ideal wire. But the fact that it's coiled this way has a very important implication, which we won't understand until in a few weeks when we learn about magnetic fields. But it turns out that when you have a piece of wire like this here and you coil around and you send a current to this wire, the current will produce a magnetic field. And because of the magnetic field that exists inside the coil here, it turns out that these wires, when it's coiled like this, these inductors, they have a very, very special property, which is that they don't like when you try to change the current very quickly in a circuit. So what happens is that if you have a constant current, let's say the current flowing here in the wire here is a constant with respect to time, just a constant current, then the inductor doesn't care, it doesn't offer any resistance, and it's as if you have an ideal wire. So for a constant current, an inductor behaves as if it's an ideal wire. But if you take the current and you change it with respect to time, okay, so you just do a change of the current, you change the value. It turns out that because of the magnetic field inside the inductor will react to that. And it reacts in the following way. If you change the current, the inductor here will oppose it work against the change of the current. So it will react by opposing the change of the current. And how does it do that? It actually creates an electric potential across the terminals of the inductor. So the inductor here starts here and then ends here. So there will be a voltage that will appear between here and here when you change the current with respect to time. If the current flowing here is constant in time, the voltage is zero. But if you change the current with respect to time, there will be a voltage between this point and this point. And what's important is that the voltage that will appear between here and here is proportional to the rate at which the current is changed with respect to time. So if you try to take the current and you try to change it very, very quickly, there will be a big voltage that will appear here and here, and that will try to keep the current from changing. If you change the current very, very slowly, very, very gently with respect to time, so let's say decrease or increase the current very slowly, then the inductor here will create a very small voltage. So it will resist a little bit, but not much. But if you try to change the current very quickly, then the inductor will work against that, and there will be a big voltage that will appear here and here. So the inductor, what it does is that it works against the change of current. You try to change the current very quickly, the inductor will react very, very strongly. We'll see the equations in a minute. Now, in terms of drawings, there are several drawings, but the ones we're going to use is either this form here or this form here for an inductor. So when you draw that in a circuit, you mean that there's a little inductor there. We won't use the other form here, although you might see them if you do more advanced electronics circuits later on in your career. But for now, we just use this symbol here for an inductor. Okay, what's the equation? Well, I told you that the voltage depends on the rate at which the current changes. And here is the key equation. Okay, this is the key equation for inductors. The voltage across an inductor is equal to a constant. This constant L here is called the inductance of the inductor. this L is not a length. Okay, we'll see what it is in a minute. It's a constant that depends on the inductor you're working with, but it has nothing to do with the length of the inductor. Okay, something totally different, but it's a constant. And the voltage, the key point is that the voltage across the inductor is proportional to the derivative of the current. So if the current changes very, very quickly, di dt would be very big, and you get a large voltage across the inductor. If you change the current very gently with respect to time, di dt would be very small because the change is very slow, and then you'll have a small delta V. If the current is constant, you have a constant current in your circuit, di dt is zero, and there's no voltage across the inductor. So when the current is constant, the inductor acts as if it's an ideal wire. It offers no resistance, there's no potential difference, so it's like an ideal wire when the current is constant. But if you change the current with respect to time, there will be a voltage that will appear across the terminals of the inductor. Okay, so we'll see how that works soon. So just again, L is not a length, it's called the inductance of an inductor, like we had capacitance of a capacitor or resistance of a resistor. What are the units? Well, if you look at the equation, clearly, okay, this side here, this is in volts. And here, if you look at this part here, this is ampere per second. So the units of L must be such that this equation works. So the units of L must be volts times seconds per ampere. So the inductance L is in volt second per ampere. Okay, so because it's a messy unit, the people decided to give it a new name, and it's called a Henry. Now this is always, people find that funny to use Henry for a unit, but it's named after, again, obviously, an American physicist this time who lived from at the beginning of the 19th century. So Joseph Henry. So we give the inductance in Henry. That's the unit. Okay, but it stands for this here. Okay, now just an interesting point to notice. Now we have three type of components: resistors, capacitors, and inductors. For resistors, we have Ohm's law. The voltage across the resistor is proportional to the current, right? For capacitor, we have delta Vc is the charge over the capacitance. Now, notice that we can also relate this to the current, because the charge is the integral of the current with respect to time. So this equation we can write in that form. Okay, that's exactly the same equation. We have that this part here, the integral of I times dt, this is just Q of t, is the charge accumulating on the place of the capacitor. So you see that the voltage across the resistor is proportional to the current. The voltage across the capacitor is proportional to the integral of the current, and the voltage across an inductor is proportional to the derivative of the current. So we have the current, we have the integral of the current for the capacitor, and we have the derivative of the current for the inductor. So you see clearly the analogy between the different elements. They react differently to the current because the resistor cares about the value of the current, the voltage across the capacitor cares about the integral of the current, and the voltage across the inductor depends on the derivative of the current. Okay, so we'll look at this equation in more details now for the inductor. Okay. Now, if you notice, if you look at these equations again, notice that the voltage across the resistor is proportional to the current, and the voltage across an inductor is proportional L times the derivative of the current. So you expect and for the capacitor, the voltage across the capacitor is proportional to 1 over the capacitance times the current. So this is why when we add resistors in series, the rule for the resistors in series is you add them up, right? The rule for the capacitors in series is you add the 1 over C1 plus 1 over C2 and so on, and you take that to the -1. So, and the reason for that is because in the resistor we have R, but we have 1 over C for the capacitor. That's why the rules for resistor for series parallel was flipped compared to the rule for capacitors, because capacitors, the capacitance appears as 1 over C. If you go back to the inductor, we're back to L here multiplying the derivative of the current. So this is analog to, is closer to what we have for a resistor. You have R here, you have L here. So because of that, I won't do the proof, but in series, the rule for inductors, when you combine them, is exactly the rule you've seen for resistors. The equivalent inductance is just the sum of the inductance of several inductors when they're in series. In parallel, you have the rule that you use for resistance in parallel. The equivalent inductance is just the sum of the 1 over the inductance, and you take all that to the minus 1. So this is the same rule as what we had for resistors. Okay, and of course, inductors in series, they have the same current flowing through them, and inductors in parallel have the same voltage across them. That's true for any elements in series or in parallel. Okay, now let's look at a very simple circuit with an inductor. Okay, so here we have, for the first time, okay, you have a battery here. By the way, this is a common notation for batteries. People sometimes put several like this here, but this is the same as when we draw just a long side here and a short side here. Okay, but there's this convention here of sometimes using this symbol here. And here they use Vs instead of EMF, but that's the voltage of the source, which is just the EMF, the battery's voltage. Okay, simple circuit. You have a switch here, you have a resistor here, you have an inductor. No capacitor for now. If there were no inductors in this circuit, let's say you remove the inductor here, you just put a wire here, you replace by an ideal wire. What will happen to the circuit? Just a resistor and a battery. When you close the switch, at the instant you close the switch, the current goes from 0, it was 0 before, it jumps right to the value that you calculate, which is, if you have just a resistor here and a Vs here, the current is just Vs over R. Okay, so the current will jump from, as you close the switch, goes from 0 to, it jumps right away to Vs over R. So you'll get a graph like this. If you plot I of t versus time here in this circuit, again, I'm assuming there's no inductor here. You start with 0 current and it jumps very, very quickly, it's almost instantaneous, to a value which then remains constant at this value here, right? So it basically jumps, it's almost instantaneous here, it jumps from 0 up to that value and then it remains constant. That's if there was no inductors. If you put an inductor, what happens? The inductor does not like the current to change quickly. So if you were in this region here, the inductor would not care. It would say current is constant, I offer no resistance, so there's no potential across the inductor here when the current is constant. Delta V here would be 0. But here, at that instant here, just when you close the switch, the current wants to jump to that value very quickly, and the inductor reacts very strongly to that. So actually, at that instant, just when you close the switch, the inductor there will be a large voltage across the inductor, just so that the current will stay equal to 0. So what happens is this. Okay, we're going to solve it. Here I'm just explaining the basic ideas, but we're going to actually solve the equations later on. But here, this is just qualitative. Okay, if there's an inductor present, just when you close the switch, the inductor reacts by opposing the change. And actually, what happens, the inductor, at the instant you close the switch, the inductor will stop the current completely. Okay, the inductor says, no, you want to jump from 0 to Vs over R. You want to have a huge change of current in a very, very short time. I don't like that. I'm going to keep the current equal to 0 at equal just when you close the switch. How does it do that? Can the inductor keep the current well, stop all the current in the circuit? Well, if there's a Vs here, with this is positive and this is negative terminal, the inductor must create a potential here exactly opposite to Vs, so equal to Vs with the opposite polarity here. So the battery is pushing here with the value Vs, pushing the positive charges this way, and the inductor, just at t equals 0, is pushing the charges with the same voltage in the opposite direction. So at t equals 0, just when the switch is closed here, you have a voltage here equal to Vs, canceling exactly this voltage, and the current is 0 at t equals 0. But then if you wait a very, very long time, okay, this is just true at t equals 0. But after a very, very long time, well, after a very, very long time, you expect the current to be constant in the circuit. Then at that instant, after a very long time, the inductor will say, okay, the current is constant, I'm fine with that. As long as you don't change the current, I don't care. And the voltage across the inductor will be zero after a very, very long time. So the current becomes constant after a very long time. So the voltage across the inductor is zero, because remember, the voltage across the inductor is L times di dt. So if I is a constant, di dt is zero. So after a long time, the voltage across the inductor is zero. And then, because there's no voltage across the inductor is acting like an ideal wire. So what you have, if you look at the circuit, if you replace the inductor by an ideal wire, what you have? You have a battery with a voltage Vs and a resistor R. So the current is just equal to Vs over R. This is the current you have after a very, very long time. So just to summarize, just when you close the switch, the inductor stops all the current. So at t equals 0, when the switch has just been closed, the current is 0. After a very, very long time, the inductor offers there's no voltage across the inductor anymore, and then the current reaches Vs over R. So look at this is also what we had when there was no inductor. If there's no inductor, you have a current equal to 0, you close the switch, and the current jumps to Vs over R. The difference now is that you close the switch, and then the current stays equal to 0 for a very short time, and eventually it goes to Vs over R. But the increase would be much more gradual because of the inductor. So what you have is a curve like this. Okay. Again, remember what we would have if you have, let's say you have, let's say if there was let's say no inductor. Okay, 1 second. If there was no inductor at all, what would be the curve? The curve would be you'll jump here right straight to this value, the voltage of the battery over R, and then stay constant. Because of the inductor says when you close the switch, it offers a lot of resistance, and then the climb would be much more gradual, and eventually you will reach E over R. Okay, this is when you have an inductor. So this is the curve here. This curve here, jumping right to this value here and then being constant. This is the curve when there's no inductor, and this is the curve when there's an inductor here. So that's it. Well, there's an equation here. Don't worry about the equation. We're going to derive it in our practice problems. So even if you cannot read them, don't worry about that. We'll derive that. But that's what an inductor does. It opposes the change. So when you close the switch, just an instant you close the switch, the inductor stops all the current. But if you wait a very, very long time, the inductor acts like an ideal wire. This is the opposite of a capacitor. If you had the capacitor here instead of the inductor, what would the capacitor do? So if you had the capacitor here and replacing the inductor, okay, instead of the inductor here with some capacitance C, when you close the switch, at the instant you close the switch, when the capacitor here, if it's initially uncharged, it offers no resistance. So at t equals 0, the capacitor acts like an ideal wire, and after a very long time, the capacitor blocks all the current. The inductor does the exact opposite. Just when you close the switch, the inductor acts like, it stops all the current just when you close the switch. And if you wait a very, very long time, it acts like a wire. So it's exactly the opposite of what we had for a capacitor. Okay, so we'll do problems in class to get used to that and see how that works out in details. Thank you.